Okay, so this morning we're going to talk about chemical nomenclature. We're going to talk about naming and writing formulas for ionic compounds, binary covalent compounds, and then acids. So the first half of this, we're going to really talk about ionic compounds, compounds made between metals and nonmetals, where, as you sort of recall, based upon our ideas of atomic structure and chemical bonding, metals are elements that tend to give up their electrons. They therefore form positive ions. The nonmetals gain those electrons, forming negative ions. So ionic compounds are essentially composed of positive and negative ions. And really, if you want to name an ionic compound, all you do is you name the positive ion first and you name the negative ion second. And it's actually as simple as that. Sometimes we make things a little bit more complex, where if we see like a compound is CaCl2, we want to say dichloride or something, where we put a prefix in there to tell that there were two chlorides in the formula. But in our actuality, that is not how you do it. All you do is you name the positive ion, you name the negative ion. So we're going to spend a little bit of time today talking about how do you name a positive ion and how do you name a negative ion. And we're going to go backwards. We're going to start with the negative ions. So anions are usually come from nonmetals because the nonmetals are the ones that gain the electrons to complete their outer shells, therefore being negative. And the way you name an anion is you take the root of whatever the element is that's becoming negative. So chlorine, you take chlor, oxygen, you take ox. You take the root of the name and you drop its natural ending and you replace it with IDE. So the way we name an anion is we take the root of the elemental name and we switch the ending to IDE. So that's how you get the name of it. How do you know if you just look at the name like chloride or oxide, how do you know what the charge of that negative ion is? Well, the charge of the ion is determined by the element's position on the periodic table. And so if you go to the periodic table, and we've been talking about this, and this is going to be on your test next week, so you're going to need to know this, you should be able to find any non-metal element on the periodic table, determine its number of valence electrons, and then think about how many electrons it has to gain until it reaches a noble gas configuration. And that number of electrons is going to be the negative charge. So on the periodic table, here are the metals on the left side of the diagonal line and the non-metals on the right side. And from experiment 5, if you didn't catch this on the post-lab questions, this is really significant. All these are the metals over here, and the only types of ions they form are positive ions. The nonmetals are up here. The only type of ions they form are negative ions. So we're going to focus just on the negative ions now. And at the very bottom, I have the number of valence electrons written. So if you know the number of valence electrons and you know these atoms tend to gain electrons, then if you have 7 valence electrons, you're going to gain 1 and your charge is going to be -1. If you have 6 valence electrons and you're a nonmetal, you're going to gain 2 electrons to reach a noble gas configuration. You'll make a -2 ion. And in the 5th column, with 5 valence electrons, you're going to gain 3 electrons to be -3. So group 17 always form -1 ions. Group 16, the nonmetals in that group always form -2 ions. Don't confuse that with the metals at the bottom. There's a couple of other elements here in group 16, but they would never form -2 ions because they're not nonmetals. They're metals. They would form positive ions instead. The nonmetals in group 15 form -3. And then way over there on the left side of the periodic table, we have hydrogen, which is capable of forming a negative ion. It is a nonmetal. And to fill its outer shell, it would gain 1 electron. That would give it 2 in its outer shell, which is the first energy level. And so hydrogens form -1 ions. So now if I give you an ion and its charge is going to exactly be determined from the position on the periodic table, so an oxygen ion would have to have a charge of -2. Well, its name is not oxygen ion. You drop the ending of the word oxygen off and you replace it with IDE. That's called an oxide ion. The ion of nitrogen would have to have a charge of -3 based upon its position on the periodic table. It's not called a nitrogen ion. You drop the ending off. This is called a nitride ion. So when you see the similarity here, what's really important, when you see an IDE ending, that's telling you the ion is negatively charged. There's no other way around it. If you have a negative hydrogen ion, the ending has to be IDE, so an H negative ion has the name of hydride. Okay? That's how you name negative ions that are created from the nonmetal elements in the upper right-hand periodic corner of the periodic table. That's pretty much that. Let's go to the other side of the periodic table and let's talk about how you name the positive ions that are going to exist in ionic compounds. So the elements on the periodic table to make the positive ions are the metals. And so when metals lose their valence electrons, they create positive ions. And when they do that, they'll have some characteristic positive charge that most of the time can be determined from their position on the periodic table. The way you name a cation is you just name it exactly as the metal name, which in actuality can sometimes be ambiguous, but you'll have to be able to tell in context. If they say, look at this silvery piece of sodium, well, they're talking about sodium atoms because that's sodium metal. If they say, I have some salt, it's sodium chloride, then you would infer that's an ionic compound. That would be a sodium ion, okay? So the name of the cation is just going to be the elemental name, and the charge is going to be determined from the element's position on the periodic table. Now, when we go to the periodic table and we look at where all the metals are, and here's the periodic table again, this time the metals are on the left side of the diagonal line. They're located here. You can only tell the absolute charge of a metal ion for a few selected metal ions on here, okay? And let's remember that. If you're in the first column on the periodic table, those metal atoms always lose one valence electron. They're always going to make +1 ions. We know that for sure. If you're in the second column on the periodic table, those metals will always lose their 2 valence electrons. They will always make +2 ions. Now, when you go through the F section and you go through much of the D section, we actually do not know what charge the ion is going to form because they can form more than one. So we're not going to talk about those metals in the middle of the periodic table yet. I'm only going to talk now about metals whose absolute charge can be determined based upon their column on the periodic table, which means they only form one ion. If we go over to group 11, and group 11 has copper, silver, and gold in it. There's one element in that group that only forms one possible ion, and it's not copper and it's not gold, it's silver. So on the periodic table in the D block, this is copper, this is silver. Silver only forms one possible ion. It's always going to be +1. You'll need to know that, but you can kind of tell from its position on the periodic table. We'll show you the little pattern here in a second, if you don't see it already. In the next group over, group 12, the top 2 elements in group 12 are zinc and cadmium. They only form +2 ions, nothing else. And then we get to the 13th column, the column that has boron on the top, but that's not a metal. So below that is aluminum, and then gallium, and then indium. Those 3 only form +3 ions. So on the periodic table, these are the only metals that you absolutely know their charge. And so when you name these particular ions, you just use the elemental name. The little trend over there on the right side that you have to sort of keep in mind is that when you're in the 13th column, the elements with 3 valence electrons, only 3 of them, aluminum, gallium, and indium, will form +3 ions every single time. Then go 1 column over, now you have 2 elements, zinc and cadmium, always form +2 only. Go 1 column over and you only have silver. So it's a 3-2-1 pattern. The charges are 3-2-1. So you'll need to know those. So any metal ion in any of those particular positions in the periodic table, the name of the metal ion is just its elemental name. So calcium's in the second column on the periodic table. We would expect it to form a +2 ion. What's its name? Calcium ion. Potassium's in the first column on the periodic table. You would predict the only ion charge it could form is +1. What's its name? Potassium ion. And then aluminum is in the 13th column. It's one of that set of 3, aluminum, gallium, and indium, that only form +3 ions. So if that's the only ion it's going to form, its name is aluminum ion. Okay? Now, we've talked about how we name anions and cations. Now let's see if we can put them together and name ionic compounds. So the name of an ionic compound, whenever it's given to you, is actually the most efficient way to name ionic compounds because it only gives you the information necessary to predict its correct formula. And we predict the correct formula based upon equalizing the ion charges. And I'll give you a couple of examples and I'll show you why we don't name it in a different way because that would be extraneous, okay? Let's take this compound, calcium chloride. That name is as simple as you can get. It's naming the positive ion, it's naming the negative ion. It doesn't tell you how many calciums or how many chlorides are in the formula, but it doesn't need to, because on the periodic table, calcium ions only form one possible charge, they're +2. Chloride ions only form one possible charge, they're -1. So by looking at the periodic table and knowing the charges, and you know compounds are neutral, well, you have to have 2 of the -1 chlorides to balance out with the positive 2 for the calcium. The formula has to be CaCl2. It couldn't be anything else. Here's another example. We're just naming the ionic compound by naming the positive ion and naming the negative ion. You can tell what the formula is by using the periodic table and determining the charges of sodium ions and phosphide ions based upon the columns there are in the periodic table. And you're going to need to do this on your test next week. I'll ask you what charged ions will sodium form, what charged ions will phosphorus form. You need to be able to look those up on the periodic table and determine them. If these are the charges of the two ions, the only way to make them add up to 0 is to have 3 sodiums combined with 1 phosphide. The formula has to be Na3P. So notice the names of these compounds are not calcium dichloride or trisodium phosphide. That would be extraneous writing. The word di and tri is not necessary because just by naming the positive and negative ions, you're able to determine the formula. So you'll find a lot of the things we do are really based upon what's the simplest thing we can do to have the least amount of work for us. And we're not going to write calcium dichloride and trisodium phosphide because that really isn't necessary. The name can be determined just by simply naming the positive ion and the negative ion. If we do one more example, this is maybe the hardest thing you'll ever see in trying to come up with the right formula of a compound. So if you can understand this concept, then really this isn't going to be too bothersome for you. The formula for this compound is determined by looking up the charges of barium ions and nitride ions from their positions on the periodic table. Barium ions are in the second column, they're positive 2. Nitride ions are in the 15th column, they're negative 3. And the only way you can make these charges add up to 0 is by finding a common multiple. The common multiple between 2 and 3 is 6. So how many bariums do you need to make positive 6? You need 3 of them. How many nitrides do you need to make negative 6? You need 2 of them. The formula is Ba3N2. Okay? So hopefully this isn't too bad. I want you to take a look at this next example now. If I ask you to write the formula for manganese iodide, you can go to the periodic table. You can find the charge of iodide, but where's manganese located on the periodic table?
Transition metals.
So it's in the transition metals, which means it's one of those elements that's in a position on the periodic table. We do not know what its ion charge is because manganese actually forms several different ion charges. So the problem here is we cannot name a metal ion that's in the F section, in the D section, or in the bottom of the P section. We can't name all of these other metals just by their elemental name because we wouldn't be able to figure out the formula. So we're going to now talk about the cations from all the other elements on the periodic table. And let me just go back and review those, okay? We've just been talking about if you're in the first column, you have to be +1. Second column, you have to be +2. Then if you're silver, you're +1. Zinc or cadmium, you're +2. Aluminum, gallium, or indium, you're +3. But everything else on the periodic table, they can form multiple ions. So I'm just stating that. So the metals other than group 1, group 2, and then the silver, zinc, and aluminum little groups, metals other than those can form multiple cations. So therefore, we have to come up with a more specific way to name individual cations for any given element. And let's go back and let's look at manganese then. It turns out that the element manganese can form several different ions. Manganese can form a +2 ion just by losing its outer shell s electrons. If it loses its 2 outer shell s electrons and then 1 d electron, it can make a +3 ion. If it loses its s electrons and 2 d electrons, it could be +4. It could also be +6. It could also be +7. So if we use the technique we did for the elements in columns 1 and 2 and just name these by their elemental name, then this guy's name is manganese. This is manganese. This is manganese. This is manganese. And this is manganese. And that could kind of be confusing because now you don't know what ion you're talking about. They all have the same name. Does that seem like a problem to you? It's a problem to chemists. They don't want to name 5 different things with the exact same name because there's no way to identify them. It wasn't a problem for this guy. This is George Foreman. He was the heavyweight champion of the world back when I was a kid. And he's more famously known now as the inventor of the George Foreman grill, which you may know somebody that has one. George Foreman has a wonderful family. This is a picture of his family. He has a bunch of sons. This son is named George Foreman. 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 I'm having a sneaking suspicion that George Foreman wouldn't have a problem naming all of the different manganese ions, manganese, 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 manganese. But fortunately, George Foreman is not a chemist. He's a boxer and an inventor and an entrepreneur. As a chemist, we can't actually have all these ions have the exact same name, so we need a way to distinguish them. And so the way chemists have decided to distinguish them is by writing the elemental name manganese and then following that with a Roman numeral in parentheses that's equal to the charge of the ion. So the way chemists differentiate the 5 different manganese ions or the multiple different ions of any chemical element that's a metal is they're named with their charge, written in parentheses after the name of the element. So the top ion there, the manganese positive 2 ion, is named manganese 2. And the way it's written is with a Roman numeral 2 in parentheses. The next one's name is manganese 3, written with a Roman numeral 3 in parentheses. The next one's called manganese 4. You'll have to know your Roman numerals, right? Roman numeral looks like this, right? That's 4. So that would be called manganese 4. An interesting phenomenon about manganese 4 is many years ago when I went to the Coliseum and I went in one of the aisles at the bottom, and much like stadiums today, like if you have a ticket and your seats are in section 31, you're going to find the entranceway that says section 31, right? Well, the Coliseum has numbers etched into the stone right above each of those little archways there. And over here, you can see above this archway, this is archway number 4. If your seats are in section 4, you see how it's written? I. It appears the Romans didn't write their Roman numerals the way we do it today, which is really interesting. I had heard that the reason for that was that the god Jupiter, his name was spelled in the original Roman letters as IV, and they didn't want to have the beginning of the god's name written on the side of the Colosseum, and they thought that'd be bad luck, so they decided to rewrite the 4 as I. And later, when Jupiter's influence disappeared, people went back to the IV. But nonetheless, I think we won't worry about Jupiter and we'll write it IV. For manganese 6, it would be with a V and an I written in parentheses, and manganese 7 would be written with a V and an I and an I. So now we actually have a way to identify each different cation of a particular element. So these parentheses are only used when you're in this region of the periodic table where the metals have multiple cations they can form. You don't use it for group 1, you don't use it for group 2, you don't use it for silver or zinc or aluminum, but you use it for all the other positions on the periodic table. So now if we go back to our compound that we had named manganese iodide before, well, that's an inappropriate name. Manganese is not the name of any cation. We would have to name that cation manganese 2 or manganese 4 or manganese 7, whatever it happens to be. So here's how you would see the name of that compound actually written. It would say manganese 2 iodide. So the 2 doesn't tell you how many of anything. The 2 is the charge of the manganese. So you look at the periodic table, you can see the charge of iodide. You can't see the charge of manganese. Well, the name tells you it's positive 2. And now that you know that, you can determine the formula of the compound to balance the charges. It would have to be MnI2. And if you have this compound, this is saying the manganese ion in this compound has a positive 4 charge, and we know iodide is negative 1. And so therefore the formula for this compound would have to be MnI4. If that makes sense, why don't you take about 45 seconds, don't say it out loud, but see if you can write the formula for this ionic compound. And if you can do that, then we'll continue on with some more challenging examples. Cobalt's an element in the middle of the periodic table, a transition metal, and you cannot tell what kind of ion it forms because it forms multiple different types of ions. But in this compound, the ion that's bonding is a cobalt positive 3 ion. Sulfide from the periodic table would always have a charge of negative 2, and the only way to determine the formula for this compound is to get a common multiple of 6. You would need 2 of the cobalt 3 ions and 3 of the sulfides. Its formula would be CO2S3. Okay.
Professor?
Yes, go ahead.
Just a quick question. They always form positive, correct?
The metals always form positive ions.
Okay, so we wouldn't need to worry about cobalt 3 being -3. It would always be.
That would be impossible.
Okay, just making sure.
Okay. If we look at this one, uranium 6 oxide, they're telling you the uranium ion in this compound is +6. From the periodic table, the oxide ions are always -2. You figure out what's the least number of ions of each that are going to make the charges add up to 0. And if you just had 3 oxides, they would add up to -6. So this formula has to be UO3. Some of us in previous chemistry classes may have learned some trick where you flip the charges and you make the 6 go with the oxide and the 2 go with uranium, and you'd have a formula U2O6, but that's not an empirical formula. Ionic compounds are always given as the simplest ratio between the positive and negative ions. So if you do flip them and get U2O6, if you can reduce that down to UO3, that would actually give you the right answer. But I just like mathematically looking at the 6 and the -2 and go, what do I need to do to make those equal to each other? I need 3 oxides. There's the formula. Okay.
I like your way much better.
Here you go. Okay. So very mathematical. If I give you the name of this compound, iron oxide, what do you think the formula for this one's going to be?
We can't tell because it's a transition metal.
Exactly right. This is a bogus name. So as you're doing your activity today, if there's anything that's bogus on there and I give you something that isn't named properly, you make sure you tell me on the activity day and go, hey, this is a bogus name, because there's something lurking for you to see if you're paying attention or not. Okay, lovely. Let's see if you can name these compounds if I give you their formulas. Let's go the other way around. If I give you this compound, if you recognize it's a metal and a non-metal, then it's an ionic compound, and that's what we've been talking about. So everything we've done up so far today has always been metals with non-metals. They're ionic compounds, and the way you name them is just name the positive ion, name the negative ion. So the positive ion's name is strontium. As long as we know, strontium always makes one charge only. And where's strontium on the periodic table? It's in the second column. So strontium only forms +2 ions. If a metal atom only forms one possible ion, its name is just its elemental name. So SR's name is strontium. F is a negative fluorine ion, so we switch the ending to IDE, that'd be called fluoride. Just name the positive ion, name the negative ion. This is strontium fluoride. Notice the spelling in fluoride, the U comes before the O, and if you don't do it that way on the activity, I will mark it wrong. Okay. This is a compound between a metal and non-metal as well. Potassium's on the left side of the periodic table, oxygen's on the right side of the diagonal line. So this is an ionic compound. Just name the positive ion, name the negative ion. Now, the K is potassium. Is the name of this ion just potassium, or do we have to put a charge in parentheses in its name? Can you tell what charge ion potassium makes every single time?
+1.
It's in the first column, so it's always +1, so no Roman numeral in parentheses. Its name is potassium. The oxygen ion in the negative form is called oxide. This compound is just potassium oxide. Okay. This one is an ionic compound. It's a metal with a non-metal. Gold is a metal. Iodine is a non-metal. So we're just going to name the positive ion and name the negative ion. Au is gold. So if its name would be gold as long as gold only forms one cation. Does gold only form one cation?
No, it forms 3.
So that means that gold cannot be named gold. We have to include its charge in parentheses. So this is the first one that's not in one of the columns. We know the charge of the metal for sure. So now you have to figure out what charge is gold in this particular compound. So what you do is you look at the negative ion in the compound, which is iodide. There are 3 of them. So they're each -1. If you have 3 -1s in the formula of the compound, the gold has to be +3. So the name of the cation in this compound is gold 3. The name of the anion is iodide. So the name of this is gold 3 iodide. Okay, does that make sense? That's when you have to use the parentheses. It's when you have a metal that forms more than one possible cation. Now, why is the symbol for gold Au?
Right, the what? Sorry?
Why is the symbol for gold Au and not G? We don't have any G's on there. That would have really been good if we could just use G for that.
Or its Latin name?
This comes from its Latin name. Yeah, its Latin name is aurum. So they have the symbol from that Au. A lot of the elements that have their symbols from Latin roots, iron's another one, ferrum, a lot of times you'll see them name the ions of gold or the ions of iron with their old Latin names. The gold 3 ion is sometimes known as the auric ion. So you may actually see this written occasionally. This is called auric iodide because the gold 3 ion is called auric. There's a lower charged gold ion that's gold 1, and that's called aurus. So they use the IC ending for the higher charge and the OUS ending for the lower charge. But we're not going to hold you responsible for any of those old Latin names, but if you do see them, that's really what it means. And if a metal forms 2 different cations, it's an IC ending for the higher charge and OUS for the lower charge. Recently, Sean Connery passed away. He was the original 007 in the first Bond movie back in the 1960s, and this was one of the first James Bond movie ever made. Do you know who he's standing with here in this picture?
Goldfinger.
Goldfinger, of course, yeah. And on the beginning scenes of the movie when Goldfinger was mad at some girl and completely, I don't know what he did with her, dipped her in gold. I'm not sure. Really kind of interesting special effects back at the time. But at one point when James Bond met Goldfinger, Goldfinger told Bond his first name. And if Ian Fleming's the one that wrote all the Bond novels, so you can appreciate Ian Fleming's humor when he did. His name is Auric Goldfinger, so he's actually called the Gold 3 Goldfinger, really, if you think about that. That was kind of cute, I thought, but most people didn't quite catch on to that. So let's look at another example. Let's do this ionic compound. This is made up of a metal and a nonmetal. The metal is lead, the nonmetal is bromine. The way you name the lead ion would just be lead, as long as lead only forms 1 possible cation. Now, look on the periodic table. Can lead just form 1 possible ion? If it does, what's its charge? Or does it form multiple ion charges?
Multiple.
So because it can form more than 1 ion, we can't name it lead. The name of this compound is not lead bromide. So you have to figure out what the charge of the lead ion is in this particular compound. It's bonding to bromide ions, which are each -1. There's 2 of them. They add up to -2. So the lead ion must be +2, so its name is lead-2. So this is lead-2 and then bromide, okay? Here's the compound that I always put on tests when I teach Chem 3, because this is the one they always miss. So 85% chance you'll get this wrong. What do you think the name of this compound is? If you're not looking at the answer there by looking at the slides.
Copper oxide.
So the only problem with that is that copper is in the transition metal section. It can form more than 1 possible cation. So if you just call the ion copper, I don't know what its charge is.
Copper 2 oxide?
So copper 2 oxide, right? Which is what everyone would say, because look at that formula. Ooh, there's a nice shiny 2 right after the copper. I bet it's copper 2 oxide. But you have violated the rules for determining how to name that copper ion. We want to put the copper ion's charge, not how many there are. What are the copper ions bonding to? An oxide ion. What's the oxide ion's charge? -2. So what does the charge of each of the copper ions have to be?
2 plus?
No, because +2 and +2 would add up to +4.
+1.
Has to be +1 each. So the name of the copper ion in this compound is copper 1. This compound's name is copper 1 oxide. Got that? Is that okay? So when you have ionic compounds between metal ions and non-metal ions, all we're doing is we're naming the positive ion, naming the negative ion. The negative ion just ends in IDE. The positive ion is the elemental name of the metal. Unless it can form more than 1 cation, then you put its charge in parentheses.
Wait, Professor.
Yep.
So since oxygen has 2 negative, and then
How many coppers are in the formula?
2.
What should the charge of each of those be? So when they add up to -2, it makes a neutral compound.
Okay.
+1, right?
Yeah.
UBN. Now, sometimes ionic compounds will contain a positive ion or a negative ion that is not just the ion of an individual element from the periodic table. Sometimes the positive and negative ions in an ionic compound could be a polyatomic ion. So we're going to talk about some of the polyatomic ions, how they're named, and then we'll work on some compound formulas that have ionic polyatomic ions in them. There are a few cations that are polyatomic. There's not very many. Here's a couple of them. The first one you'll eventually have to know. On handout 1, where it gives you the list of the 56 elemental symbols I will expect you to know for your first exam, like hydrogen is H, helium is He, 56 of them you should know. The second page of handout 1 also gives you a list of the polyatomic ions you'll need to know eventually for test 2. You'll need to know the first one on here, NH4 with a +1 charge, is a group of nonmetals that covalently bond together, but they don't make a neutral molecule. They actually have lost an electron. They therefore have a +1 charge. So this is a positive ion. It's a cation that's made up of multiple atoms. So it's called a polyatomic ion. Its name is ammonium. So anytime you have a group of atoms that are bonded together, but they have a charge to them, they're called a polyatomic ion. And some of them are positively charged. UO2 is a +2 polyatomic ion. It's not very common. I didn't put it on your list of polyatomic ions to memorize, but I was like putting on here because who wouldn't like saying the word uranyl over and over again? So that's kind of weird. But the other positive polyatomic ion, that was an unfortunate name, huh? The other polyatomic ion I would like you to know is this one, because this is unique. This is actually a polyatomic ion of 2 metal ions that have bonded together. Of all the metal ions that exist, sodium ions, iron 2 ions, potassium ions, aluminum ions, there's only one metal ion in the universe that does not exist individually. And that's these guys. These are mercury 1 ions. Mercury 1 ions, if they bump into each other, bond together to form a diatomic ion. So there's 2 mercury ions in the formula. They add up to +2. So each mercury in this formula is a mercury 1 ion. So this is called mercury 1. So you're seeing all those shiny number 2s there, and you go, shouldn't this be named mercury 2? But no, it shouldn't. Those mercuries are not +2 each. If they were, the total charge would have been +4. These are mercury 1 ions. So I have this on the list of polyatomic ions for you to know because the mercury 1 ion always comes in pairs, and if I have you memorize it, it's one thing you'll remember, okay? Now, most of the polyatomic ions are actually negatively charged, so they're anions. And when you have an anion, we always have a special ending for them. If you have a negative chlorine ion, it's called chloride. A negative oxygen ion, it's called oxide. Well, if we have a polyatomic ion that's negative, we're going to have to use a special ending, but it's not going to be IDE. We're going to use ATE or ITE. And this is what indicates to you the polyatomic anion contains oxygen. So you name any polyatomic anion that contains oxygen as the root of the element that's bonding to the oxygens, and then you make the ending ATE or ITE. So for example, carbon can bond with several oxygens, and it will not form a neutral molecule every single time. Sometimes it'll form something with a charge. The first thing here written is CO3 2-. So this is not a molecule, this is a polyatomic ion. Nitrogen can bond with oxygens to form neutral compounds, or they can form this species, NO3, with a negative charge. That's a polyatomic ion. So how do we name these? We take the root of the element carbon or the root of the element nitrogen, and we tack on at the end ATE. This is called carbonate. NO3 minus is called nitrate. All right? So when you have a particular element on the periodic table bonding to a number of oxygens and it makes a negatively charged ion, those are going to wind up having ATE endings. Phosphorus will form a polyatomic ion with oxygens. Sulfur will form a polyatomic ion with oxygens. Their names are phosphate and sulfate. So these are on the list of polyatomic ions for you to know on the end of handout 1, and you'll need to know those for test 2. And in fact, what we're going to have when we finally return to campus the week of February 22nd. So for some of you, you'll be on campus Tuesday, February 23rd, and some of you Thursday, February 25th. That will be the date of our only quiz of the semester. It's going to be a nomenclature quiz where I'm going to give you 20 compounds, and I'm going to either give you the name and you write the formula, or give you the formula, you write the name, and you'll have to get 17 out of the 20 right to pass. And if you don't pass, then the next time we come to school, you will take the test again. And we'll just offer it as many times as we need until we hopefully get you to pass. Otherwise, I'll see you in Chem 1A again next semester. All right. Now, this quiz will take place on campus. And so I will give you just a blank periodic table and the exam itself. So you will not have a list of elemental symbols or polyatomic ions. So by the time we take that test in a couple of weeks from now, you will need to know those polyatomic ions. Otherwise, it's going to be really hard to write the formula of a compound that has carbonate in it if you don't know what carbonate is. Now, I said polyatomic ions end in ATE or ITE. These are all the polyatomic ions that end in ATE. You're going to see these on handout 1 for you to memorize. But most of these elements can also make a secondary polyatomic ion with one less oxygen. Nitrate is NO3 minus, but nitrogen can also form a polyatomic ion whose formula is NO2 minus. Charge is the same, but there's one less oxygen. How do we name this? For a lesser number of oxygens, you switch the AT ending to ITE. This is called nitrite. Sulfur not only bonds with 4 oxygens to make sulfate, it can bond with 3 oxygens to make another polyatomic ion, same charge. We need a different name for that. So with one less oxygen, we switch the ATE to ITE, okay? And so now if I'm gonna have you learn 10 or 12 different ATE ions, I've secretly had you learn 10 or 12 different ITE ions because they're only just one oxygen less, okay? Now there are a few elements on the periodic table that can form more than 2 polyatomic ions with oxygen. Some can actually make up to 4 different oxy ions, and I have one of those on handout 1 for you. Chlorine can actually bond with 4 oxygens, 3 oxygens, 2 oxygens, or 1 oxygen. So they form 4 polyatomic ions with oxygen, and we actually have a systematic way to name each of those so they each have their own unique name to them. One of them you're going to memorize because it's going to be the ATE ion with chlorine. That'll be called chlorate. That happens to be this one. So if you memorize that ClO3 minus is chlorate, we will now give you the systematic way to figure out the name of ClO4, ClO2, and ClO. What does ClO minus have to be named? The one right below it.
Chlorite.
Chlorite, there you go. So we're halfway done. So now what we need to do is we need to figure out a way to name ClO4, which has 1 more oxygen than chlorate, and a way to name ClO, which has 1 less oxygen than chlorite. So for the ClO4, if it has 1 more oxygen than chlorate, we're going to take the same name chlorate, but we're going to put a prefix in front of it that means more than. And if we have any biology majors out there, and if you've actually done some biology, if you ever worked with cells in different solutions, if a bunch of cells are sitting in a solution, if it has a salt concentration higher than the salt concentration of the cells themselves, what type of solution is that? What do you call that?
Hyperchloric?
Hypertonic is what the solution's called. Hyper means more than, and we're going to use that in front of the chlorate to mean more oxygens. In fact, we're not going to use hyper. We're going to drop the HY off and just put per. But from that same concept, if you put per in front of chlorate, that's telling you 1 more oxygen than the chlorate ion. So ClO4 minus would be named perchlorate. Now, if ClO2 minus is chlorite, and we have ClO that has 1 less oxygen than chlorite, what do you think would be a prefix we could use that mean less than? It would be just like if you had a salt solution that had a lower salt concentration than the cells. What would that kind of solution be called?
Hypotonic.
Hypotonic?
Hypotonic. Hypo is the prefix we use, so ClO minus we call hypochlorite. So there's not very many elements that form 4 different oxy ions. The halogens mostly do. Chlorine, bromine, and iodine will form a set like this. But if you had any other polyatomic ion, like if you had nitrate, NO3 minus, well, if there was an NO4 minus, it would be called pernitrate. There's an NO2 minus, it's called nitrite. And if there's an NO minus, it would be called hyponitrite. So this pattern would apply to any element that forms a series of 4 oxy ions. They all don't necessarily, but if they did, then that's how that would work, okay? Now, for the biology majors, you're probably in love with all of this because I've given you handout 1 and I've asked you to memorize the whole thing, and biologists love memorizing things. But if you're an engineering major, you're going, wait a second, I'm an engineering major because I like concepts and figuring things out. I don't want to memorize a bunch of stuff, otherwise I would have been a biology major. So if you're an engineering major, let me give you a little way that you might be able to get around a little bit of memorization. And if you're a biology major, you can go to sleep for a few minutes. There's a number of elements on the periodic table that will form polyatomic ions with oxygens. Here's a bunch of them. They would form borate, carbonate, nitrate, silicate, phosphate, sulfate, chlorate. How could you figure out what their formulas are? Because there didn't seem to be any rhyme or reason to them. The nitrate had 3 O's and a -1 charge, but the phosphate had 4 O's and a -3 charge. They all seem to be arbitrary and capricious. Well, here's a little trick you can do. If you take each of these nonmetals that could bond with oxygen to form a polyatomic ion, and you imagine, this has to be an imagination, so Mr. Osenian, don't get me wrong on this, this doesn't really happen, but if these nonmetals actually form positive ions, which they don't, right? If they did and they lost their valence electrons, what would be their positive charges? Well, I've got their number of valence electrons written right at the top, right? Boron would lose 3 valence electrons and be +3. Carbon and silicon would lose all 4 electrons and be +4. Nitrogen and phosphorus would be +5. Sulfur would be +6. Chlorine would be +7. So if you just imagine that in a fictitious world were to happen, then the way the polyatomic ions are created is these elements with these charges bond to a certain number of oxygens. If you're a small atom and boron, carbon, and nitrogen are in the second row on the periodic table, so they're small atoms, then the ATE ion is going to be the one where boron, carbon, or nitrogen can only bond to 3 oxygens. It's not big enough to get any more around them. So borate is BO3, carbonate is CO3, nitrate is NO3. But the bigger atoms in the next row, silicon, phosphorus, sulfur, chlorine, they bond with 4 O's to make the AT ion. So silicates SO4, phosphates PO4, sulfates SO4. Does that make sense? Okay, so now engineering majors, because you're so good at math, let's figure out what the formula of borate would be. If borate is a boron with 3 oxygens, and the boron has a +3 charge, and the oxygens, you would give them their natural negative charge of -2. So the 3 oxygens are -2, -2, -2 is -6, but the boron is +3. Add that up, it's BO3, 3 negative. Now, is that right or not? Does it always work? Let's try the carbon one, because we saw the carbonate ion just a couple moments ago. If carbon is +4, and it bonds with 3 oxygens that are -2, -2, and -2, +4 and a -6 come out to be an overall charge of -2, that's the carbonate ion, CO3, 2-. And nitrate is NO3-. And if we go below that to the phosphorus, which it's going to bond with 4 oxygens because it's a bigger atom, the phosphorus is +5. The 4 oxygens added to -8. 5 and -8 is -3. Phosphate is PO4, 3-. It exactly works. Okay, so if you're not a good memorizer, but you're taking the nomenclature quiz in a couple weeks and you can't remember carbonate, nitrate, phosphate, or sulfate, well, there's a way you can figure it out if you follow that little pattern there, okay? So just a little hint if you're looking for some order out of this seemingly random naming of polyatomic ions. So now let's look at some ionic compounds that contain polyatomic ions, show you how you write their formulas, how you read their names, etc. So here's one, sodium bicarbonate. There's 2 words here because an ionic compound is made of a positive ion and a negative ion. So the first word's the positive ion, second word's the negative ion. Sodium is a positive ion, we know its charge is +1. Bicarbonate ends in ATE, that's telling you it's a polyatomic ion with oxygens. Right now, you may not know what that is, so you'll probably need to refer to handout 1. And if you look it up, it's HCO3, and it has a -1 charge. So because the 2 ions here are equal but opposite in charge, we only need 1 of each. So the formula is NaHCO3. If I ask you what's the name of this compound, the name or what is written in words at the top, sodium bicarbonate. If I say what's the formula of the compound, that's the elemental symbols, NaHCO3, okay? This one, the barium is the positive ion in the compound, the hydroxide's the negative ion. Barium from the periodic table is a metal that forms only +2 ions. There's no element hydroxium, so that hydroxium is not from an element. That must be a polyatomic ion. There are some that end in IDE. And if you look it up, the hydroxide ion is OH with a -1 charge. So the barium is +2, the hydroxide's -1. To get the right formula, we would need 2 of the hydroxide ions. It would be wrong to write the formula BaOH2, because that looks like 1 barium, 1 oxygen, 2 hydrogens. If you need 2 of a particular polyatomic ion, or 3 or 4, you have to put it in parentheses with a 2 on the outside. Does that make sense? This now says 2 O's and 2 H's. If you leave the parentheses off, it says 1 Ba, 1 O, and 2 H's. That would be wrong. If I asked you what's the name of this compound, you would say barium hydroxide. If I asked you what's the formula of the compound, you would say BaOH taken twice. And the way I read that is I had a dramatic pause between the positive ion and the polyatomic ion. Listen again. Ba OH taken twice. So you can tell there are 2 hydroxides in there. You don't want to say BaOH taken twice, because I can't tell what's taken twice. And we don't say BaOH2, because that sounds like 1 O and 2 H's. So it's BaOH taken twice. We use the parentheses if there's more than one of a polyatomic ion. In our first compound right here, sodium bicarbonate, there were not 2 bicarbonates, there was only 1 bicarbonate, so we didn't use parentheses. Now, if you put parentheses, would it make it wrong? Not necessarily, it would have the same meaning, but it's extraneous writing, and we don't want to do extraneous writing. Now, in the old days, you may not know this, but tennis rackets used to be made of wood. And so when I would take my tennis racket down to the tennis court, I would ride my bike down to the court. The tennis rackets, you would always keep screwed together with a bracket like this, because if it was made of wood, it would tend to warp. And if your tennis racket warped, then your shots go flying all over the place, right? So when you go to the tennis court, you'd ride your bike down there with your bracket on your racket, and then you'd sit outside the tennis court, you'd take the bracket off, you'd leave it with your bike, and you'd walk onto the court with only your tennis racket. Because let me tell you, it was a social faux pas to walk onto a tennis court with the bracket on the racket. Does it make you a bad tennis player? No. Is it wrong to do? No. But is it unacceptable? Apparently it was, so nobody ever did it. So with that in mind, if you look back at this compound here, NaHCO3, would it be wrong to write parentheses around HCO3? No, it doesn't make it wrong. But let me tell you, if you go to UCI or you go to UCLA or you go to Cal State Fullerton or wherever you transfer to, and you're in a chemistry class and you write Na parentheses HCO3 close parentheses, they're going to look at you and go, where did you learn to write that? And that's where you better say, I learned it at OCC. That's where I went. Yeah, OCC. Let's try this one. Iron 3 nitrite. The iron 3 ion has a positive 3 charge. The name is telling it to you. Nitrite's a polyatomic ion. On your list of polyatomic ions, we have nitrate listed as NO3 minus. Nitrite must be NO2 minus. So the charges here are +3 for iron, -1 for nitrite. So the only way to get a neutral compound is to have 3 nitrites. So because I need multiple numbers of the polyatomic ion, I will use parentheses. So the formula will be Fe, and then you write NO2 in parentheses with a 3 on the outside. If I ask you what's the name of the compound, its name is iron 3 nitrite. If I ask you what the formula is, you would read it this way. Fe, NO2 taken 3 times. All right, hear the pause there. Fe, NO2 taken 3 times. If you're a fan of Old English, it's perfectly acceptable to say Fe, NO2 taken thrice. But not that very many people say that, but you can do that if you wish, if you're a rugged individualist, okay? Let's try going the other way around. Let me give you the formulas of some ionic compounds, see if you can tell me what the names are. Going back to the very first moment of our lab period today, name the positive ion, name the negative ion, end it. So for this compound, LiNO3, you should recognize Li is the positive metal ion, NO3 is a negative polyatomic ion. If you don't know your polyatomic ions, and you're going to name this lithium nitrogen trioxide because you think there's 3 different components, but there's really only 2. There's the lithium ion, and lithium only forms +1 ions, so its name is just lithium. NO3 is a polyatomic ion, that's called nitrate, so the name of this compound, by naming the 2 ions, is just lithium nitrate. Okay? In this particular ionic compound, we have a positive ion, and then our negative ion is a polyatomic ion. You'll have to look that up. That's the cyanide ion. So we would name the positive ion, we name it cobalt, unless cobalt can form more than 1 cation. Does cobalt form more than 1 possible ion?
Yes.
So that means we can't name it cobalt. So we have to include its charge in the name. So now we have to know what the charge of the cyanide was. Cyanides are -1 each. There are 3 of them. They add up to -3. So the cobalt must be +3. So the name of the cobalt ion is cobalt 3. The negative ion is cyanide. So the name of the compound is cobalt 3 cyanide. And that's how you handle ionic compounds. Any questions up to this point? Okay. Have you ever been to the East Coast in the summertime and you go to a restaurant and you get the salt shaker and you try to shake the salt out and it doesn't come out? Ever happen to you? It'll happen if you go to Europe in the summertime too. That would happen to anybody. You're not world travelers. Okay. So what's happened is in the salt shaker, you have formed an ionic compound known as a hydrate. A hydrate is an ionic compound that has absorbed water molecules from the air, and the water molecules kind of make the salt crystals dissolve together a little bit and they stick. And so they don't come out of the salt shaker. So these are ionic compounds that have water molecules trapped in their crystals. And therefore it leads to some bad effects if it happens to table salt, because you can't get the salt out of the salt shaker. So next time you're on the East Coast or in any really humid place and you're at a restaurant, take a look at the salt shaker. You'll notice they put little grains of rice in there because rice absorbs water more than the salt does. So the rice absorbs the water, the salt doesn't. So the salt can come out more easily. But what an ionic compound will do, if it does absorb water from the air, is it'll absorb a stoichiometric amount. It'll absorb a certain amount of water and then it'll stop absorbing that. And we can actually, in a chemical formula, indicate how many water molecules get absorbed by each formula unit of the ionic compound. So we can actually name these by naming the ionic compound, then indicating the number of water molecules that get bonded to each formula unit. So the way we name a hydrate is we name the ionic compound first, just what we've been doing for the past 50 minutes. Then we use a prefix for how many waters get bonded to that formula unit. And then we follow the prefix with the suffix hydrate. So to name hydrates, you need to know the prefixes we're going to use for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for 1, 2, 3, 4, 5, if you have one water molecule, the prefix would be mono. 2 would be di, 3 would be tri. These kind of make sense to you. Hey, on your phone, remember we used to have that game where those blocks would drop down, you try to eliminate the bottom rows, and you have to move them around. What was that game called?
Tetris.
Why was it called Tetris?
4 pieces, 4 blocks.
There's always 4 blocks of dropping. 4 is the prefix tetra, okay? 5 is penta, like the Pentagon outside of Washington, D.C.
Petrus.
Hexa. 7 is hepta. 8, like an octopus, is octa. 9 is nana. That's probably the most common one missed. A lot of times I get nana for that, but nana's my grandmother. And so I don't want you putting my grandmother for 9 waters, put nana, not nana. And 10 would be deca. So if you know these prefixes, then let's see if we can practice writing the formula for an ionic compound from its name and then a name from its formula. Okay, so with those in mind, here's what a compound's name would look like if it's a hydrate. We say the ionic compound name first, copper 2 chloride, and then what does it say after that? A prefix followed by the suffix hydrate. So if you're dozing off right now and not really paying attention, then when you see that hexahydrate, you won't have any idea what that means when you see it on the activity today. But it's telling you the number of water molecules because hydrate stands for waters. So first you have to write the formula for the copper 2 chloride. So copper 2 means copper's positive 2, chloride is negative 1. The formula for the ionic portion of this is CuCl2. Then hexa means 6. There are 6 water molecules bonded to that formula unit. So what you do is you put a dot in the name and it's written CuCl2 dot, a big old 6, H2O. And that says 6 water molecules get attached stoichiometrically to every copper 2 chloride formula unit. And that's how you write the formula for a hydrated substance. Let's try going the other way around, where if I give you the formula, could you tell me what the name is? So you would first name the ionic part, so we forget the 9 waters. So we have Fe with NO3 taken 3 times. Iron's a transition metal. It can form more than one possible cation, so I can't just call this iron nitrate. Iron's name has to have a charge in it. The nitrates are -1 each, and there's 3 of them, so they add up to -3. So the iron would have to be +3. So that's called iron 3 nitrate. That's the ionic portion. And then we name the 9 waters. So how would you name 9 waters?
Nonahydrate.
There you go. So it's iron 3 nitrate, nonahydrate. Does that make sense? Okay. Mr. Julian, look at the name we just wrote for that second compound. Is there a dot in the name between nitrate and nonahydrate?
There is not.
Yeah, I don't see one either. Is there a dot in the formula?
There is.
Yeah, so guess what I'm going to do if you put a dot in the name on your activity today?
Drop us from the class.
I'll probably have to drop you from the class. I mean, it's only common sense. So don't put a dot in the name. Look at these examples. There's a dot in the formula. There's no dot in the name. Is that all right? Good. Mr. Julian, good answer. Why do you quit? Okay.
Can you put a dot at the end? No, I'm just kidding.
Arsenian's really pushing the envelope here. Okay.
Sorry, don't want to get dropped.
That's right. Don't want to be dropped. So we've talked about ionic compounds. Now we're going to spend a little bit of time talking about two types of covalent compounds. There's millions of types of covalent compounds. Organic chemistry is an entire class on covalent compounds made with carbon. But we're going to talk about how you name simple covalent compounds made of two elements, and then covalent compounds that are called acids. So if a covalent compound is made of only two elements, it's called a binary compound. It's because there's two elements in it, binary. And when you have a covalent compound, because they share electrons, they do not form ions, an element's position on the periodic table tells you absolutely nothing about what type of covalent compound it's going to form. The fact that oxygen is in the 16th column and might make -2 ions doesn't help me in figuring out how it bonds with other nonmetals. So because the periodic table is not useful, the only way we can indicate what the formula of a binary covalent compound is by using prefixes to tell how many atoms there are of each element. We have to do it. There's no other choice. So the way you name a binary compound is you name the first nonmetal, whatever it is in the formula, just as its elemental name. If there's more than one atom of it, you will use one of the prefixes we just talked about in terms of hydrated substances. So you name the first nonmetal. If there's only one atom of it, just say the elemental name. But if there's more than one atom, you would need to use a prefix. Then you name the second nonmetal and you change its ending to IDE, and the second nonmetal always uses a prefix. This is actually the simplest way scientists have determined to name binary covalent compounds so that the name can tell you what the formula is. So let me show you a couple of examples. You probably actually already know the name of this compound. What's that compound called?
Carbon dioxide.
Dioxide.
You just followed the rules for binary compounds. You named the first element as its elemental name, but there was not more than one of them, so you only said carbon. And then the second element, you switched its ending to IDE and you used a prefix, dioxide. So those are the rules for naming binary covalent compounds. What's the name of this binary covalent compound?
Carbon monoxide.
So you name the first element as its elemental name, you name the second element with IDE and always use a prefix on the second element. And so you're actually sort of familiar with this. If I give you this one, the only tricky thing here is there's two atoms of the first element. So if there's two atoms of the first element, you have to put di in front. This is dinitrogen, and then you always use a prefix for the second one, monoxide. Notice for monoxide here, they didn't say monooxide. If there were two O's in a row, they dropped one of them and just sort of merged them together like that. Okay, so this is actually fairly elementary. We only have to spend like 30 more seconds talking about binary covalent compounds because I want to go the other way around. I want to give you some formulas, see if we can calculate what the names are for that. So the way you calculate what the formulas are is you just look at the prefixes. They tell you exactly how many atoms of each element there are. This says phosphorus triiodide, and triiodide, they put two I's in a row. If they say phosphorus, that means one atom of phosphorus. Let me point out something. You see the word phosphorus? It ends RUS. So make sure you spell phosphorus correctly when you have elemental phosphorus. So that means one phosphorus, one P in the formula. How many iodides are in the formula?
3.
Right. Sometimes people get confused and they go, gee, iodine's diatomic, so maybe they mean 3 I2s, so there's 6 iodides. No, that's not true. Triiodide means 3 individual iodides. The formula is PI3, not P, I2 taken 3 times. Okay. Why don't you take 20 seconds and see if you can write down the formula of this binary covalent compound. And if you can do that, then we'll move on to the final type of compounds, which are the acids. So this should be telling you 2 arsenic atoms and 5 sulfur atoms, As2S5. All right, that's how you name binary covalent compounds. How do I know they're covalent? Non-metal with non-metal. I probably should have mentioned that earlier just to make sure we're understanding this, right? Non-metal, non-metal. They're both on the right side of the periodic table. So if you have two non-metal atoms that are bonding, it's not an ionic compound. So you don't use name cation, name anion. If it's two non-metals bonding, that's a binary covalent compound. So you use prefixes to tell the number of atoms of each element in the compound, okay? The last type of compound we're going to talk about are acids. And acids were substances that people had known for a long time. They knew a lemon had this like sour taste to it. And so whatever was in that lemon, they started calling that acidic, and limes have the same kind of thing, and vinegar, they all have these acidic type properties. But what was it that was making vinegar and limes and lemons acidic? Well, the Swedish chemist Svante Arrhenius in 1884 believed he identified what chemical species was causing substances to be acidic, and were also causing other substances to be basic, which are materials that neutralize acids. So he proposed the first definitions for acids and bases. And you will need to know this for test 2 for sure, not test 1 though. So the Arrhenius definition of an acid is any compound that if you dissolve in water, that compound will somehow release hydrogen ions from its formula. They'll float around in the water, and those hydrogen ions are what gives the solution their kind of sour taste to them. So we call this an Arrhenius acid. It's a compound that loses hydrogen ions in solution. And there were other things that can neutralize acids. Those were called bases. They're actually kind of slippery feel. They're bitter in taste. Bases were good at clearing out drains. They can dissolve soap scum and stuff like that. Well, what was it that was causing bases to have their slippery and bitter type properties? Well, Arrhenius identified a base as any compound that when you dissolve it in water, it releases hydroxide ions into the solution. It's the hydroxide ions that are giving the solution its basic properties. Okay. Arrhenius did a lot of things. If you continue all the way through Chem 1B and stuff, you'll see his name crop up at least 2 more times. But Arrhenius, who did this in the 1880s, this was the beginning of the Industrial Revolution. Arrhenius was the first person to recognize that, gee, we're starting to burn a lot of fossil fuels, and that's going to release a lot of carbon dioxide. So we have the potential of increasing the amount of carbon dioxide in our atmosphere, which is a molecule that retains heat. And so we actually could start warming up the planet. He was the first one to actually realize that that was an actual possibility. So multi-talented person in a lot of different areas of chemistry. Now, what we're going to talk about is how you name acids, okay? And if an acid is not dissolved in water, it's really not an acid yet. So out of water, acids have been historically named as ionic compounds, although that's actually a lie. An acid, and if you think of any acid you might know, like maybe HCl, if you've been in chemistry before, that's a hydrogen and a chlorine. Those are 2 nonmetals. They share electrons. They actually form a covalent compound. But if you have HCl, it's going to be named as if it were ionic. And HCl, when it's not dissolved in water, is actually a gaseous material. So this HCl gas, how would you name that? You would name it hydrogen chloride as if it were an ionic compound. Really a misnomer. You should name it as a binary covalent compound. It should be hydrogen monochloride, but nonetheless, historically, this is where we are with that, so that's what we're stuck with, okay? So when a compound with H's in them, and this is an important thing to realize, how do you know something's an acid? Well, if it loses hydrogen ions in solution, what should it have in its formula? A hydrogen. So they put the hydrogens at the beginning of the formula to help you indicate that, oh, I think that's an acid, as opposed to writing a formula like this, CH4. If you put the hydrogens in the back of the formula, CH4, then people look at that and go, oh, that probably is not an acid. It probably doesn't release the hydrogens, it holds on to them, so that wouldn't be an acidic material. But if they write HCl in this fashion, because the H is in the front, then just by first approximation, you would think if I dissolve that in water, maybe those hydrogen ions would be released. For the Arrhenius bases, just to point this out, they must be compounds with hydroxides in them. So they would be things like sodium hydroxide or potassium hydroxide. And those are just ionic compounds. They actually are truly ionic compounds, metals with non-metal polyatomic ion. And so we just name them as the rules for ionic compounds, sodium hydroxide, potassium hydroxide. There's no special way to name bases. But when you take the compound HCl, whose name is hydrogen chloride, and you dissolve it in water, we want to give it a different name because now it's in solution, it's released its hydrogen ions, and it has a whole different concept than HCl, the gas. So we're going to talk about how you do that, and the way you name acids is very systematic. There's only 3 possible names an acid can have, and you just have to learn this little technique, and once you got it, this will be really easy. But for some of us, it takes a while before we really get this down. So we'll try to do it here today and see if we can make this make sense to you. So when dissolved in water, something like HCl, its name is going to be based upon the acid's anion. Okay, so semantically, let's make sure we understand what I'm saying. Acids are something like hydrogen bonded to chloride. Chloride would be the anion. So the name of the acid is going to be based upon what the anion that the hydrogen is bonded to. And here's how it works. When you have an anion, think about all the negative ions we've talked about today. We've talked about things like chloride, nitrate, phosphite. Every single anion we've talked about today either ends in IDE, ATE, or ITE. That's it. Every anion ends with one of those 3. So that means there's 3 different ways to name an acid, depending upon whether the anion ends in IDE, ATE, or ITE. That's it. So it's important for you to be able to recognize what's the name of the anion that hydrogen is bonded to in our little compound that's an acid. So let's say you have an anion in the acid that ends in IDE. That means hydrogen is bonded to something like chloride or fluoride or bromide. It's hydrogen chloride, hydrogen bromide, hydrogen fluoride, okay? If the acid is bonded to an anion that ends in IDE, you take the name of the anion, it could be chloride or bromide or fluoride, drop the IDE off and replace it with ic and put a hydro in the front. Every single time you take the root of the anion's name, you put hydro in the front, you drop the ide off and you replace it with ic. And then you say the word acid. Now, what if hydrogen is bonded to a anion that ends in ate, like hydrogen bonded to carbonate or hydrogen bonded to sulfate? How do you name that? Well, you just take the name of the anion, the carbonate or the sulfate, you drop the ATE off, and you replace the ATE with ic. So we take the root of the anion's name and put ic at the end. These are the 2 that confuse people the most because people love writing hydro in front of things. And so they use the rule, always put hydro in the front of the name of every acid because I really like hydro. But that would be wrong. Hydro really only belongs in the front of the name if the anion ends in IDE. If the anion that the hydrogen is bonded to ends in ATE, you don't put the hydro in the front. And once you realize that, then the clouds will part, the sun will shine, and you will understand how to name acids. But that's really the thing that throws people off the most. This last one's not so bad. The only other way an anion can be named is if it ends in ITE, like nitrite or phosphite. So if you have hydrogen bonded to an ITE ion, you name the acid with the root of the anion's name, drop the ITE off, and replace it with OUS. And what you've just written down now, or what you're looking at, is the rules for naming every single acid. There's no exception. It's always like that. Let's try a few examples, okay? So if you have an acid, and how would I know this is an acid? They have hydrogen written in the front, okay? So if I ask you, name this acid, I'm not talking about naming it when it's out of water. Out of water, that would be called hydrogen bromide. If I say name the acid, we're assuming it's dissolved in water, and I want one of the green names that are over here on the left side. So here's how you do this. You first have to identify what would be the name of that compound if it wasn't dissolved in water. So you name it as an ionic compound. So I'm going to write in green here what my brain is thinking, but this is not the answer. I would go, HBr is hydrogen bromide. Now, why do you think that? Because you have to know what the name of the anion is. And look, it ends in IDE. So if it ends in IDE, that means the name of the acid is going to be hydro, brome, ic, acid. You drop the ID off, you put hydro in the front, ic at the end, and there's the name of your acid. HBr, when it's dissolved in water, is called hydrobromic acid. It has to. That's the rule for any time you have hydrogen bonded to an IDE anion. Does that make sense? Let's try again. H2S has hydrogens written in the front. This is actually a foul-smelling gas, hydrogen sulfide, but when you dissolve it in water, it loses its hydrogen ions and becomes an acidic solution. So how do we name that? So in your brain, you go, let me name it as an ionic compound. That would be called hydrogen bromide, right? If we really named it as a covalent compound, you call it dihydrogen monosulfide, but it should be hydrogen sulfide, not bromide. I misspoke. So this name written as an ionic compound is hydrogen sulfide. All you do then is you focus in on what the anion is. Oh my gosh, look at this. It ends in IDE. So you're going to drop the IDE off and you're going to write hydro, sulf, ic, acid, bada bim, bada boom. Okay. Now, there's a couple of elements that when you write their names as acids, they stick an extra syllable in there. Sulfur is one of them. So although theoretically hydrosulfuric acid is exactly correct, they actually say hydrosulfuric acid. And so anytime you have an acid with sulfur in it, I want you to stick the extra in there, and you call this sulfuric acid, and this one specifically hydrosulfuric acid. Phosphorus is another one that does that. You'll see when we do an example of acids with phosphorus, we'll stick an extra syllable in the name. So you just have to get used to hearing that so that you know that's how you do it. Okay? Let's try this. This is, if we name this as an ionic compound, hydrogen bonded to nitrate. So that's hydrogen nitrate. So how would you name HNO3 when it dissolves in water? Because when it dissolves in water, it's now an acidic solution because it has the hydrogen in the front that it releases. Well, the anion name ends in ATE. So what do? You drop the ATE and replace it with ic, and you're done. This is called nitric acid. People love to call that hydronitric acid. I don't know why. I think they really like writing hydro in front of things. But if you have an ATE ion, you absolutely do not write hydro in front of it. You just replace the ate with the ic, and that would be called nitric acid. Okay? This has hydrogen bonded to the sulfate ion. So the name of this compound, if it's not dissolved in water, would be hydrogen sulfate. How do you name H2SO4 when it dissolves in water as an acid? Because the anion ends in ATE, you take the ATE, you drop it off, and you put ic, and this would be called sulfic acid theoretically, but its actual name is
Sulfuric acid.
Sulfuric acid.
uric acid, exactly right. Does that make sense? Okay. It doesn't seem so horrible, does it? How bad can it be? Let's try this one. Hydrogen's bonding to some polyatomic ion. If I look on my list on handout 1, there's an ion called phosphate, but that's PO4. This is PO3. What's this guy's name? If PO4 is phosphate, this must be phosphite. So the name of this compound, when it's not dissolved in water, name it as an ionic compound, hydrogen phosphite. All right? So if the anion in the acid ends in ITE, you go down here and you pull the ITE off and you put OUS instead. That would be phosphorus acid. But as I said a couple of moments ago, phosphorus is another element like sulfur where they actually stick an extra syllable in there. So it's actually called phosphorus acid, right?
Professor?
Yep.
How come some of the hydrogens have 3 in the subscript and some have 2 and some has 1?
Acids are neutral compounds, so whatever the charge of the anion is, you need an appropriate number of hydrogens to balance that out. The phosphite ion has a -3 charge. That's why it needs 3 +1 hydrogens to make a neutral molecule. Make sense?
Yes, thank you.
Earlier, like a bromide was -1, so we only need 1 hydrogen to neutralize that to make HBr. One more thing about the spelling here. Notice phosphorus acid, it ends OUS because we put an OUS on there. So that's how you spell phosphorus acid. But what if I wanted to spell the element phosphorus? Remember the element phosphorus? No O in there. So there's a difference between the element phosphorus and then this phosphorus acid. Let's try going a couple examples the other way around, and I think we'll be done for this morning, and the rest of the time you just can work on finishing your activity. So if I give you the name of an acid, and I want you to come up with the formula. Now we just have to work this backwards. You go, if this says hydro and ic, you have to figure out what the hydrogen is bonded to in this acid. Because as soon as it says acid, you know the compound has hydrogen bonded to something. Sometimes that skips our mind. When you see acid at the end, that means this is a compound of hydrogen bonded to something. You're just trying to figure out what the hydrogen is bonded to. So with the ic and the hydro, you go, where's ic and hydro here? Here it is, hydro and ic. So what does that mean the hydrogen's bonded to? It's bonded to an ion that ends in IDE. So the hydrogen must be bonded to fluoride. So you would think in your head, this is hydrogen fluoride, okay? Now, what's the formula for hydrogen fluoride? Now, getting back to what Mr. Holmes just asked a moment ago, you have to make a charge balance. Hydrogen ions from the periodic table in the first column would be +1. Fluoride ions from the 17th column are -1 because they're +1 and -1. We only need one of each. So the formula would have to be HF. That would be hydrofluoric acid. Okay? You heard of hydrofluoric acid before?
Isn't it highly acidic?
It's actually not highly acidic, but it's highly dangerous. If you ever saw the TV series Breaking Bad, then they use hydrofluoric acid to like dissolve dead bodies and stuff. Yeah, it's really vicious stuff. It actually attacks calcium in the bones, and you get that exposed to it, you actually can die. And so no schools ever have hydrofluoric acid around. It actually was really bad, but not because it's so acidic. There's other acids that are actually more acidic than that. It just attacks you in a different way because of the fluoride ions. Let's try this one. Let's see if we can get the formula for carbonic acid. So you got to go, okay, it's an acid. Hydrogen's going to be bonded to some anion. What anion is it bonded to? The name has an ic in it. So let's see, here's an ic right here, but oh no, that has hydro on the front, not that. Here it is, just the root of a name with ic. So what is the hydrogen bonded to? An ATE ion. So that means hydrogen must be bonded to carbonate. So the acid is hydrogen bonded to carbonate. And now for Mr. Holmes to figure out the formula, hydrogen ions are +1. A carbonate ion is -2. So you have to make the charges add up to 0. You need 2 hydrogens to bond with 1 carbonate to make a neutral molecule. Okay?
Wait, Professor.
Yep.
What was the charge for hydrogen again?
Hydrogen's in the first column on the periodic table. So when hydrogen's going to be positive, it will lose its only electron and be +1.
Okay.
Okay?
Professor, how did we get CO3 on that? Carbonate is...
Because you
Sorry, I didn't
eventually
get that.
have memorized carbonate as CO3. But the way we got it is we looked at the name of the compound was carbonic acid. So you have to go, if the acid ends in ic, what's the hydrogen bonded to? It's bonded to an ATE ion. So that means hydrogen must be bonded to carbonate. And then in 2 weeks from now, you will have memorized carbonate is CO3 2-. And that's how you'll do that. Right now it's on handout 1. So if you recognize that the acid has carbonate, look up its formula and charge, but in a couple of weeks from now, you should have that memorized.
Thank you, Professor.
Let's try one final one. If I give you nitrous acid, this is going to be hydrogen bonded to some anion. So you have to figure out what the anion is. If the name ends in OUS, that tells you explicitly the anion must end in ITE. So in this compound, hydrogen is bonded to nitrite. So the acid is actually the compound hydrogen nitrite. Hydrogen is +1 from the first column on the periodic table for Mr. Martinez. And nitrite is a polyatomic ion. You'll need to know its formula and its charge. Now, handout 1 gives you the formula and charge of nitrate, which is NO3-. Well, nitrite would just be 1 less oxygen, so NO2-. And if hydrogen's +1 and nitrite is -1, you only need 1 of each. The formula would be HNO2. Okay? And that's how that works.